Ever get a little intimidated by some of those multivariable calculus terms? It can sound pretty complex, right?
Oh, definitely.
Well, today we're tackling one that sounds like it's straight out of a sci-fi movie, the Jacobian matrix.
Ooh.
But don't worry, we've got all the audio lecture snippets and visual aids all lined up to really try to demystify it.
Sounds good. It's actually a bit like, using a GPS. But instead of navigating roads, the Jacobian helps us navigate how functions change when we have multiple variables involved.
Okay, I'm definitely intrigued.
Yeah.
So we're talking about going beyond just like y equals some function of x, right?
Right.
What kind of real-world situations are we talking about when we bring in this multivariable action?
So think about something like trying to predict the weather.
Okay.
You don't just need to know the date. You need location, right?
Yeah.
You need latitude and longitude. And even then, it's not like the weather report is just one number.
Right.
You've got temperature, humidity, wind speed.
Right. Multiple things to measure.
Exactly. So multiple inputs leading to multiple outputs.
So it's like comparing a single thermometer reading to a full-blown weather station report.
Exactly. And the Jacobian matrix is what helps us understand how, tweaking those inputs, like, say, moving a few miles north or east, will affect each of those outputs.
So if regular derivatives, tell us about change in a simple function, the Jacobian is like their multi-talented cousin who can handle the really complex stuff.
Yeah, you could say that. It's about seeing the bigger picture of change in multiple dimensions.
All right, so we're convinced it's useful. But how do we actually find this Jacobian matrix? I'm guessing it's not as simple as, looking it up on a map, right?
Right. It's not quite that easy. It's actually a matrix. So picture a grid of numbers.
Okay.
And each entry in that grid is a partial derivative.
Ah, partial derivatives. For anyone who's just tuning in, that's where you act like all the other variables are kind of frozen in time.
Right.
While you see how just one input affects just one output.
Exactly. It's like fine-tuning each ingredient in a recipe separately to see how it changes the final flavor. And then by arranging all these partial derivatives in the right way, we get our Jacobian matrix.
So we're essentially breaking down a complex relationship into smaller bite-sized pieces.
Exactly. And the source material gives us a really cool example using polar coordinates like you see on a radar screen and transforming them into our familiar Cartesian coordinates, the x and y axis kind of graph.
Right, because even switching between those two ways of plotting a point, that's a function in itself.
Precisely.
Yeah.
And when we actually go through the steps to calculate the Jacobian matrix for that specific transformation, something really fascinating emerges.
Okay.
It actually helps us see how areas change when we switch between those coordinate systems.
Hold on, area's changing. So it's not just about individual points moving around. It's like we're stretching or shrinking the whole grid.
You got it. Think of it like taking a shape, like drawn on a rubber sheet and stretching that sheet in different directions.
Okay.
The Jacobian matrix kind of tells us how much that stretching or shrinking is happening at every single point.
That's wild. So we've gone from this abstract idea of a Jacobian matrix to understanding it's about change in multiple dimensions. And it reveals something fundamental about how areas distort when we transform between systems.
Exactly. And this concept of area changing is huge, E.
Okay.
It's not just about flat maps and radar screens. Think 3D animation.
Oh, wow.
Medical imaging, even analyzing distortions in astronomical observations. It pops up everywhere.
Okay, now I'm really feeling the power of this thing.
Yeah.
But the source material mentions something about this area-changing business not being just a fluke with polar coordinates. There's a deeper principle at play here, right?
Absolutely. It all comes down to something called the Jacobian determinant.
All right, so we left off with this intriguing Jacobian determinant. It sounds important, but for our listener out there, why should they care about this determinant?
Well, think back to that rubber sheet analogy.
Okay.
The Jacobian determinant tells us exactly how MUCH, a tiny area on that sheet, gets magnified or shrunk when we stretch it using our function, right?
Okay.
It actually gives us a measure of that distortion.
So it's if the determinant is 2, then a tiny square on our sheet would double in size after the transformation.
Yeah.
And if it's 0.5, it would shrink by half.
You got it. And this whole concept isn't just limited to 2 dimensions.
Right.
Imagine a 3D object being projected onto a 2D screen, like in computer graphics.
Okay.
The Jacobian determinant can actually help us understand how volumes change during that projection.
Oh, okay. Now that is a cool visual.
Yeah.
But the source material also hinted at a connection between the Jacobian and something else that might sound a little familiar, the chain rule.
Right.
And suddenly I'm having flashbacks to calculus class.
Awfully good flashbacks, though.
Yeah, hopefully.
Remember, the chain rule helps us find the derivative of a composite function like a function within a function.
Right.
It turns out that the Jacobian plays nicely with the chain rule, even when we're dealing with multiple variables.
Okay, so instead of just a chain of functions, we might have like a whole network of interconnected functions, each with multiple variables.
Precisely. And instead of a single derivative, we've got like the Jacobian matrix to represent the change in each variable. But the beauty is, the chain rule still works. We can actually use Jacobians to like break down these complex systems and understand how a small change in one variable will like ripple through the entire network.
So it's like having a map, not just of the roads, but like of all the traffic patterns and alternate routes. So we can kind of predict the impact of like an accident or a detour.
That's a great way to put it. And this is incredibly useful in fields like machine learning, for example.
Okay.
Where you might have like hundreds of layers of functions all working together.
Wow.
The Jacobian can help us understand how like tweaking one parameter in the system will ultimately affect like the final output.
It's like fine-tuning like a really complex recipe.
Right.
You need to know how changing a pinch of salt in one part of the process will, ultimately affect the flavor profile.
Exactly. Now, the source material, it kind of delves into this concept of differentiability.
Okay.
And it sounds obvious, but what does it actually mean for like a multivariable function to be differentiable?
Right, because it's not as simple as just like drawing a smooth curve like we could with like single variable functions.
Exactly. One way to think about it is to like break down the multivariable function into its component functions.
Okay.
Remember those partial derivatives we talked about?
Yeah.
If each of those component functions is differentiable at a point, then we can say the whole multivariable function is differentiable at that point.
Okay.
It's like saying, if every ingredient in a cake is mixed well, then the whole cake batter will be smooth, right?
Okay, that makes sense. But the source material also hinted at another way to think about differentiability that's maybe a little more mind-bending.
Yeah.
It mentioned something about a magic matrix.
Right. So it's about finding a way to like approximate the change in the function's output based on like tiny, tiny changes in its input.
Okay.
Essentially, we're looking for like a linear transformation that best captures how the function behaves locally.
So we're like zooming in on a map until a curvy road looks straight.
Exactly.
Yeah.
And the fascinating thing is that the magic matrix that achieves this best linear approximation is the Jacobian matrix itself.
Wow.
It's like this single tool helps us understand both the big picture of like how areas distort and the very local behavior of the function.
Wow, it's like realizing your tour guide is secretly like a code breaker. So the Jacobian can tell us how differentiable a function is, and even help us find that best linear approximation. That's impressive.
Yeah.
But how does this all connect back to our earlier discussion about areas and those stretching transformations?
That's a great question.
Yep.
And the source material actually kind of illustrates this beautifully using, again, our polar to Cartesian transformation.
Oh,
Remember how we talked about the Jacobian determinant being related to how much areas change?
right.
It turns out that the absolute value of the determinant tells us the exact scaling factor for areas as we make those like tiny, tiny transformations.
So if we take an infinitesimally small square in the polar coordinate plane and transform it using our function, the ratio of its area to the area of the corresponding shape in the Cartesian plane is basically equal to the absolute value of the Jacobian determinant at that point.
You nailed it. It's like saying the determinant is a measure of how much we're zooming in or zooming out as we switch between those coordinate systems.
Like looking through a magnifying glass,
Yeah.
the Jacobian determinant tells us the magnification power.
I like that analogy. And here's the kicker. This concept isn't just limited to these like specific coordinate systems.
Okay.
It applies much more broadly to, any differentiable functions, any transformations between different mathematical spaces.
Oh.
It's a fundamental principle.
Okay, my mind is officially blown. So we've got this Jacobian that helps us understand change in multivariable systems. It reveals how areas distort. It connects to the chain rule. It even tells us how differentiable a function is.
Right.
Is there anything this mathematical powerhouse can't do? It sounds like we've uncovered a treasure chest of mathematical tools. But before we get too carried away, is there anything else lurking in the depths of the Jacobian matrix? It feels like we've only scratched the surface.
And you're right to think there's more. The source material actually touches on something called directional derivatives.
Okay, now those ring a bell, but maybe a little faintly. It's like you're finding the slope of a surface, but instead of just going in the X or Y direction, you can pick any direction you want, right?
You're exactly right. Imagine you're hiking up a mountain. The directional derivative tells you how steep the climb is in a specific direction. And as you might have guessed, the Jacobian matrix can help us calculate these directional derivatives without, getting bogged down in trigonometry.
Okay, that sounds incredibly useful. I remember those calculations being a bit tedious back in calculus class.
Right. Well, the source material, it points out a really elegant relationship. The directional derivative is essentially the dot product of the gradient vector and the unit vector in the direction you're interested in.
Oh, the gradient vector.
Yeah.
That's like a vector that points in the direction of the steepest descent at a particular point, right?
Precisely. It's like if you dropped a marble on a surface, the gradient vector would tell you which way it would roll.
Okay.
And again, the Jacobian matrix helps us find this gradient vector without breaking a sweat.
So by connecting the Jacobian to directional derivatives, we're essentially getting, like, a more complete picture of how a function changes, not just in general, but in any specific direction we choose.
Exactly. It really highlights how, interconnected all these concepts in multivariable calculus are, It's not just, a jumble of formulas,
Right, yeah.
but rather, a beautifully woven tapestry of ideas.
I love that analogy.
Mm-hmm.
So we've explored how the Jacobian helps us understand change, distortion, differentiability, now even directional derivatives. It really is like a Swiss Army knife for navigating the world of multivariable functions.
That's a great way to put it. And, while we've focused on some concrete examples here, the real power of the Jacobian matrix is its versatility, right?
Okay.
It pops up in physics, engineering, economics, even image processing.
Wow, it's amazing to think that this one mathematical tool has such far-reaching applications.
It really speaks to the power of mathematics as a language for describing the world around us,
Well said.
Mm-hmm.
So as we wrap up our deep dive into the Jacobian matrix, what is the one key takeaway you want our listener to walk away with?
If there's one thing to remember, it's this. The Jacobian matrix isn't just some abstract mathematical object. It's a powerful lens through which we can view and understand change in all its complexity.
Okay.
And that understanding has the potential to unlock some incredible insights in countless fields.
I love that. And for our listener out there, here's something to chew on. We've mainly focused on functions with a handful of variables.
Mm-hmm.
But imagine a function that takes in the state of every neuron in your brain as input and outputs your next thought or action.
Yeah.
To talk about a complex system, I think understanding the Jacobian of that function would be quite the deep dive, wouldn't it?
Definitely.
Well, that's all the time we have for today. Thanks for joining us for this deep dive into the Jacobian matrix.